Okay, let's talk about our reaction for this week, the Wittig reaction. So today, we'll have our two reactants, mix them together at room temperature, let them sit for 15 minutes, then we'll end up with our product of interest here at the left, and a co-product as well. Before we go into some details about the protocol, let's talk about why the Wittig reaction is important in the first place. So chemists frequently use this reaction to make complex organic molecules. For example, if we were to synthesize vitamin A in the lab, we could use the Wittig reaction to do so. The structure of vitamin A is included here on the slide for you. You can see it's quite complicated. And vitamins such as vitamin A are essential for human life. Particularly, they're essential in the growth and development of children. But for adults as well, they're really important for a healthy immune system. Finally, vitamin A is important for eyesight. Vitamin A can often be known as retinol, retinal, and so it is essential for eyesight. If you think about maybe some anatomy you know about the eye, you could recall the retina at the back of the eye. It's named after this molecule because this chemical is essential and a part of the proteins in the back of the eye that allow you to see light. Oftentimes, if you have a vitamin A deficiency, a side effect could be blindness. Let's talk a bit about the procedure. This reaction will happen at room temperature for 15 minutes without a catalyst. I want you all to think a little bit about what this means in terms of whether or not the reaction is favorable and maybe what the activation energy might be for such a reaction. In particular, as always, but particularly this week, let's monitor the reaction carefully and note any changes in color or any changes in temperature of the mortar and pestle while the reaction proceeds. We will continue and do an additional Buchner funnel filtration, but I want to emphasize here that you must use clean glassware. Make sure that vacuum flask is clean. The filtrate will be our product of interest. The filtrate is the liquid that comes through the Buchner funnel. It's going to go into the flask. This is why we need that flask to be clean. Finally, since our product is in the filtrate, and as a part of the filtrate we will have dissolved our product in hexanes, we need to get that hexane out of there so we can see how much product we have. A rotovap will be an excellent way for us to do this. This is probably many of our first time using the rotovap, and so I'm happy to explain that to all of you in the lab. Generally, rotovaps are used to concentrate product and evaporate off solvent, in our case, hexanes. So it might be important to know the boiling point of our solvent. We'll see this when we go into the lab, but the rotovap has kind of a couple different important parts. One particularly important part is a hot water bath. We're going to heat that solvent up and pull a vacuum on it so it evaporates, leaving us with our pure product. Couple of notes from last week, folks. This is new for this week, but for this week, check your protocol. It is very specific about what we want you to spot on your TLC plates. But from last week, let's make sure to make some really nice dilute solutions for TLC. You need a tiny, tiny amount of product. One tiny crystal will do, or a very small drop if your product is a liquid. Dissolve that nicely in plenty of solvent. Additionally, I recommend that everyone checks their TLC before even running it. After you spot your reactants and products, go ahead and look at your plate under the UV lamp, and you should be able to see whether or not you have a nice small spot or a rather large spot. We're going to be doing some additional fun development of TLC plates. First off, yes, when those TLC plates are done running, check them under the UV lamp. But this week we will run 2 plates to do additional development steps. I know I mentioned this last week, but we ran out of time. The first, iodine staining. Iodine vapors are drawn towards unsaturated groups, think alkenes, and aromatic functional groups, think phenyl rings. When we put our plate into an iodine chamber, you can find them on the TLC bench. We'll close that chamber, and you'll see the plate will start turning brown. The plate will be a light brown, and any spots where we have these nice functional groups will appear a darker brown. The second stain we're going to do this week is a really nice deep pink purple potassium permanganate. This stain will mark any oxidizable functional groups. Think alkenes, think alcohols, anything that can be oxidized really. You'll see these show up as a yellow spot on a purple background. The whole plate will kind of come out purple from the solution, but there'll be yellow spots. And in order to use this solution, we don't have a chamber. You'll have to be very careful with some tweezers and dip that plate into the solution. Be careful not to lose your plate in the solution, because then it'll be gone forever and you'll have to run another plate. To wrap up this week, let's talk about our next 2 green chemistry principles. And again, folks, I encourage you to include these in your conclusion. The first, less hazardous chemical syntheses. When we're working in the lab, it's really best if we are not exposed to chemicals that are toxic to us, or potentially, if they go to the waste, toxic to the environment. Think about the reaction we're doing this week. Notice which chemicals are we using that are toxic, or how toxic are the chemicals? Is it green? Is it not? The second principle this week is designing safer chemicals. So this week we're making some reaction product. We want to be making chemicals that are not toxic to us either. So yes, the reactants shouldn't be toxic, the solvent shouldn't be toxic, but also let's try not making products that are super toxic, right? I'm sure many of us have heard about the PFAS in Michigan water. That's a chemical product. And it is in our water, kind of contaminating our water for us and for the organisms that live in our environment. That is obviously a toxic product. We shouldn't be making toxic products if we can avoid it. So think about how that relates to this week's reaction. In particular, one thing that's a little bit interesting is our product of interest, right? That's what we're intending to make. But the co-product is a bit interesting because it can be used for other purposes. So this isn't exactly the same as designing safer chemicals. This is more like reusing co-products. But this co-product is sometimes used in the recrystallization of other materials as a bit of like a seed. So that's an interesting point. That's all for this week, folks. Leave you with a meme of Grumpy Cat here saying 9. 9 is German for no. And since the chemist who this reaction is named after is German, I thought this would be a nice touch. See you in lab.